Hello and welcome to a bonus episode of Physical Attraction where we'll describe just what it's like when they fire the tokamak at Jet. Now, this description of how a pulse run is actually done at Jet comes from Cullum's website at CCFE, and I thought it was a pretty good summary of how the fusion reactor actually works at present, and the various complications that can be involved. So I've preserved most of it as it's found on the website, but added a few details here and there, and I hope you enjoy it. Unlike future stations where the plasma will need to run for several hours or continuously, in Jet, each pulse typically lasts around 40 seconds. Although this might seem like a short amount of time, the 80,000 or so plasmas already created in the machine since 1983 have provided crucial information for plasma science by focusing on its behaviour and improving its performance. The pulses have all contributed to an extensive knowledge bank of data, with over 100 terabytes of data collected to date, and their analysis plays a key part in the long-term goal of fusion electricity on the grid. Like all good stories, the story of a pulse has a distinct beginning, middle and end, a strong setting, and involves many people, in this case engineers, scientists and computer experts, who all have different roles to play. Chronologically, the story begins at 7 AM in the Jet control room. This is the operational centre of the Jet facility where experiments are undertaken in 2 8-hour shifts. In this story, the first shift of the day is just starting and 15 pulses will be run in its duration. Before today's pulses can take place, scientists and engineers from fusion laboratories all over Europe have applied to carry out experiments on Jet. Their proposals have been discussed by a task force and the direction of experimental campaigns identified. A steering committee has matched the submitted proposals with the current scientific requirements of Jet, and each experiment has one science controller attached to it. Back in the control room, the first pulse of the day, a dry run, is about to take place. This is the chance early in the morning to check that all of the systems needed to operate Jet are running smoothly and a profitable day of experiments can follow. None of this can take place without the engineer in charge, the session leader, the shift technician, the scientific coordinator, and the physicist in charge all in their positions. All of these roles will become clear as the story unfolds. Having checked the status of the machine following the dry run pulse, the session leader pre-programs the next pulse. The main responsibilities they have are to prepare a realistic experiment plan, which fulfills the wishes of the scientific coordinator and their team as far as possible. Based on this plan, the session leader prepares the basic types of pulses which need to be run in a session. They will program the details of these pulses, so that's the time evolution of things like density, plasma current, magnetic field, plasma shape, into the so-called pulse schedules which contain all of the information required to run the pulse. During the shift, the session leader, starting from the prepared pulses, adapts the pulse schedules in response to the results of previous experiments and in discussion with the people who are doing the science. When they're happy with the schedule for the next pulse, they transmit the schedule to the engineer in charge, who checks that the pulse is actually safe for Jet to run. The session leader also communicates with the physicist in charge, who is responsible for setting up various diagnostic systems with the heating system operators. Before the pulse can begin, the power supplies need to be enabled. The power to make a pulse comes partly from electricity directly from the grid, and additionally from stored energy in 2 massive flywheel generators on the Cullum site, with roughly 50% coming from each source. As the flywheels are enabled in the control room, the parameters have been decided and set by the session leader and confirmed with the engineer. The engineer then ensures that the operators of the required subsystems, the power supplies, the computer systems, the heating systems and all the diagnostics are ready, and then they start the countdown for the pulse. Once this happens, a computer-controlled initialization sequence begins. After 2 minutes, the sequence is held. At this point, everyone checks that everything is functioning correctly. When they're satisfied, the shift technician triggers the pulse. They're the staff who actually pushes the red button that makes the plasma happen. At 0 on the countdown, there's a siren noise, an announcement to all in the control room that plasma will be created in Jet. 40 seconds later, the plasma is created and can be seen on a dedicated screen. A number of checks are performed automatically during the pulse, and if limits are succeeded, the control systems will terminate the plasma by gently ramping the plasma current down. The session leader and the engineer also watch the infrared cameras closely and listen attentively to any audio feedback from inside the machine. It is very unlikely, but if anything is judged not to be right, they can push a button that triggers a gentle ramp down in a similar way to the automatic stops. As most commonly happens on Jet, the pulse then goes ahead as planned. During the first 40 seconds after the end of the countdown, the currents in the large magnetic coils surrounding the vacuum vessel are ramped up to create the required magnetic field inside the vessel. The field has to be just right to allow a plasma to be created inside the vacuum vessel. At 40 seconds, a minute amount of gas, which is normally deuterium, is injected into the vessel and a strong electric field is induced, which ionizes the gas, making it into a plasma. The plasma which has now been created is a very good conductor of electrical current. The electric field initially used to create the plasma now generates a strong current in the plasma, and this current is ramped up in a controlled way to very high levels, typically 4 to 5 million amperes. The current in the plasma itself generates a strong magnetic field of its own, which adds to the magnetic field generated by the various magnetic coils, allowing the plasma to be confined without cooling the plasma down by touching the inside of the vacuum vessel. Once the plasma is well established, the detailed shape of the plasma is controlled using the poloidal coils that wrap around the tokamak. Only the edge of the plasma is visible on the screen in the control room, as only the edge radiates in the visible range of wavelengths. After a short while, a significant amount of current is put into a set of special diverter coils situated just below the plasma itself. The field generated by these coils is so strong that it's stronger than the field generated by the plasma in the vicinity of the coils. The so-called X point occurs at a position where these two fields cancel out. Magnetic field lines just above the X point will trace out donut-shaped surfaces which never get near the vacuum vessel. Just a little further out from this surface, magnetic field lines no longer form closed toruses. In fact, they all finish by hitting the diverter in the bottom of the machine, which is designed to absorb most of the power. When the X point is formed at the bottom of the machine, the diverter becomes bright, and once the plasma is in this X point configuration, additional power is applied. This power, mainly from the neutral beam injection system, puts up to 35 million watts of power into the plasma, heating the plasma up to 150 million degrees Celsius. At this point, the plasma surface, and in particular the diverter, becomes very bright and hot. A strong shaking of the image is also observed on the dedicated screen. This shaking is associated with phenomena called edge-localized modes. These edge-localized modes can be seen as small solar flares as they expel significant bursts of energy at regular intervals, typically 10 to 50 times per second. The phase with higher power lasts from 5 to 20 seconds, after which the power is switched off. Then the plasma current in the magnet field slowly ramp down, and the plasma extinguishes when this plasma current approaches zero. Once the pulse is over, up to 60 gigabytes of data is collected. Some is reviewed immediately, but most is stored for long-term analysis. The pink glow on the screen in this experiment lasted for 40 seconds. The longest pulse ever run was 1 minute long. The next pulse will then be run in another 30 minutes. Before the next pulse can begin, they analyse the behaviour of the pulse to check that it did what requested, and they use this information to determine how the pulse schedules will be worked out for future experiments. The length of the pulse on JET is limited by engineering design and cost consideration. Two main factors mainly limit the duration. The magnetic coils, although they're cooled, heat up during the pulse, and when the temperature reaches a limit, the current has to be ramped down to avoid cumulative heating over many pulses, which could cause damage to the coils. Now remember that JET still uses normal copper coils as its magnets essentially, so in future experiments where you're using superconductors, you wouldn't actually have this problem of magnet heating because there's no resistance in the magnets. But of course, if it was the case that the magnets were heated up beyond their threshold, then you do have a real problem. This duration was part of the original design, and much stronger cooling or superconducting coils would be required to extend the pulse length significantly. The second thing that limits the pulse length is the fact that the plasma current is maintained by a voltage induced in the plasma by varying the current of the main transformer coil. This voltage can only be maintained as long as the current in this primary coil varies. To get the longest possible pulse, the current in the primary coil is ramped up before the pulse to its maximum value. During the pulse, it's then ramped down at the rate required to have the desired plasma current by inducing the desired voltage. But of course, once it reaches its maximum negative value, you can't sustain the plasma current anymore because you can't generate this voltage anymore. In the design of JET, the pulse length was fixed in order to have 10 to 20 seconds at full power and field. In plasmas, most things vary on timescales of less than a second, and hence after 10 to 20 seconds very little changes in the behaviour of the plasma unless there's a disruption. This means scientists can learn almost everything they need to from plasma pulses of 10 to 20 seconds of duration, at least at first. Well, I hope you've enjoyed that bonus episode, mostly from CCFE, which has described how the plasma pulses at JET are actually run, and hopefully it will give you a slightly better idea of how these tokamak experiments are being run at the moment. Until next time then, take care.